Okay, we're going to look at resisted motion. What happens when we take resistance into account? Basically, we come down to three situations that we're going to look at, because remember, we're going to be resolving in the horizontal and the vertical direction. Now, the key thing is resistance, mentioned it before, always in the opposite direction to which you're moving, and that basically comes from the third law. So we could be moving in a horizontal line, so we resolve the horizontal component. So in which case, the resultant force, I'm saying, okay, I'm moving that way. The only forces is actually the R. So if I was to come up with the equation, I'd say, oh, well, my resultant force is negative R. I'd divide through by M and have some sort of equation then that we go and play with. We could have a vertical one, but there's two situations to consider with vertical. We might be going up, so now I'm going to say resultant positive is going to be up, but then we'd have the force due to gravity going down, as well as some resistance going down as well. So my equation would end up with mx double dot is minus mg minus r. Again, divide through by mass and you'd have some equation to work with. Just because there's resistance, it doesn't change the physics of the problem. The greatest height is still going to occur when velocity equals zero. Well, that doesn't change. But if we're going down, so now I'm going to define down to be positive. Now gravity is still going down, that's not going to change. But resistance will now be going up. So we get a slight change in my motion equation there. It's now positive mg, because it's in the same direction that we're travelling, minus the resistance. Divide through by the m, and away we go. When we have downward motion, we have this thing called terminal velocity. Now basically terminal velocity, there's two ways of working it out. Terminal velocity is the limit of the velocity as time approaches infinity. So if you could keep going forever and ever. But the quicker way of working out is usually just to say, well, look, it's going to be when acceleration is equal to zero. We're going to have upwards for this example. Initial velocity of u, and it's saying we've got resistance. Assuming that the retardation due to the resistance, fancy way of saying the force, is kv squared. Find expressions for the greatest height and the time it takes to reach that height. So all right, let's draw up our diagram. Just a point to note here, I've put the resultant force there just to remind myself, okay, I'm defining up to be positive. If they say draw a force diagram, don't put the resultant force on the diagram. So remember, it's the result of all the forces. So only put what I'm putting in red, I guess. So we'll have gravity going down, resistance is also going down, kv squared. I've just written the initial conditions down there to remind myself. So at the ground level, displacement is zero and the velocity would be u. So here's my equation. mx double dot is equal to minus mg minus kv squared. Divide through by the mass, and there's my acceleration equation that we're going to play with. I've got acceleration in terms of velocity. Now we want to find two things here. One's the greatest height and the other is time. So let's do the first bit, greatest height. So we want to link displacement and velocity together. So v to v dx, make it all one fraction on the right hand side. I can now play around with it, separate the variables, and we end up with dx is, well, the integral of dx is minus m. I pulled that out as a constant. V to v on mg plus kv squared. Okay. Well, the left hand side, that 0 to x is just going to be x. The right hand side, I want to make it look like a standard integral. I want to create 2kv because I want the derivative on top. So I'm going to create a log situation here. But if I put it on the top, I got to put it on the bottom. So I end up with m on 2k. Okay. We now have a log situation. So it's the log of mg plus kv squared. Substitute in the u. Substitute in the 0. Using our log laws, we can pull that together. And we get m on 2k. The log, well, which way do you want to write it? You can write it as mg plus ku squared on mg, leave it all as one fraction. Or we could change it to 1 plus ku squared on mg, it's the same thing really. And so that is the greatest height. Okay, there's no actual numbers there, but you know, there it is in terms of k and u and all those sorts of things. So we've found the greatest height. The next part of the problem was the time it takes to get there. Well, rather than playing with this equation, which I could because remember, dx to t is velocity, so I could try and make v the subject of this and then play around with that, but no. Let's just go back to our acceleration equation. And instead of using v to v dx, I'll now use the v to t. And that'll get time and velocity into the equation. Because I don't actually need to know what the greatest height is, because I can say, well, velocity is equal to 0. Just sub that in. All right. So we now are going to integrate on the right-hand side there to v on mg plus kv squared. We want to turn this into an inverse tan, basically. So inverse tan, I wouldn't have kv squared, I'd just have v squared. So okay, I pulled the k out, but that means the mg becomes mg on k. So inverse tan, it's 1 over a. A in this case would be the square root of mg on k. So it's 1 over that, flip it upside down, square root of k on mg. Inverse tan, square root of k on mg times v. Substitute in u, substitute in 0. Thank goodness the inverse tan of 0 is just 0, so that bit disappears. And I get this wonderful expression for the time. The square root of m on kg, the inverse tan of the square root of k on mg u. Right, let's try another one. So you've got to be real careful with the algebra, you notice. A lot of algebra manipulation in this. This time we're going to drop a body 5 kilograms from a height at which gravitational acceleration is g. We're going to assume air resistance is proportional to the velocity. Let's find an equation for the velocity after time t. So this time we're dropping it. So my resultant force, I'll say, is going down. But notice, instead of calling it mx double dot for this one, because I know it's 5 kilograms, I've called it 5x double dot. So force due to gravity will be 5g, and going up, our resistance is an 1/8 v. So divide through by the 5, we get our motion equation. We want velocity and time. So for this one, it would make sense to make acceleration to v to t. That'll allow me to link. Make it all one fraction on the right-hand side. Now we should be able to do it. Initially, well, we're just dropping it. So the initial velocity must be 0. So when t equals 0, v is equal to 0. We want to link v and t together. Left-hand side will just become t. Right-hand side, we're going to have a log situation here, aren't we? So we get minus 40 log 40g minus v. Sub in v, sub in 0. And there's our 40 log 40g on 40g minus v. But that's t in terms of v. The way the question's been asked is they want v in terms of t. Okay. So let's make the subject. Divide through by 40. Exponentialise both sides. Turn both sides upside down, because I'd rather have v in the top of the fraction. So that means my exponential now is e to the minus t on 40. Multiply by the 40g. Then move terms round, and we've got it. There it is. V equals 40g minus 40g e to the minus t on 40. You could factorise the 40g out if you wanted to. I mean, it doesn't really matter. I suppose the second last line would satisfy what they're asking for. So let's find the terminal velocity. Everybody said, well, the quick way of doing it is just to have a look at acceleration. It's going to be when acceleration is equal to 0, and solving that one, we get 40g. The other way of doing it was to look at the limit as t approaches infinity of our velocity. Now, if you have a look at velocity, e to the minus t on 40 is our backwards exponential. So therefore, the limiting velocity is 40g. So either way, you come up with the answer, 40g. Okay, let's now find how far it's fallen. So now we want an expression for x in terms of t. Well, hang on, let's go back. We've got an expression for v in terms of t. So let's use that and make v equal to dx to t. So this is what we're integrating. 40g is a constant, pull it out. But that integral is not too bad. Integrate 1, you get t. Integrate e to the minus t on 40, we'll get 40, minus 40 e to the minus t on 40, but minus minus becomes a plus. Sub in t, sub in 0, and yeah, I didn't bother factorising on that one. I suppose I could have pulled 40g out, couldn't I? But anyway. So 6d and 6e we'll use tomorrow as well.